In a recent paper titled Why Black Holes Probably Have No Measurable Tidal Deformability, theoretical physicist Boris Kgr analyzes one of the most persistent assumptions in modern astrophysics. When gravitational-wave observatories like LIGO and Virgo record the collision of compact objects, they look for a specific signature in the data, the tidal deformation of the bodies right before they merge. If an object has a structured interior, the immense gravity of its partner will stretch it. This chart displays matched filter analysis of actual strain data from stellar mass merger GW190924. Looking at the bottom right panel, the likelihood distribution for the tidal deformability parameter peaks exactly at 0. The dashed 90% confidence line mathematically supports a deformability of absolute 0. A complete absence of a measurable tidal response implies that these massive bodies do not yield to external gravitational stress. They behave as if there is no internal material to stretch. This null measurement forms the bedrock of our assumptions about black hole interiors. Astrophysicists take this zero deformability observation as definitive proof that black holes must be singular points of infinite density. But that deduction relies on a critical logical error. The standard model of a spinning black hole, the Kerr solution, predicts exactly this result. According to the Binnington-Poisson theorem, any compact object with a perfect vacuum exterior will have a quadrupolar tidal love number, or K2, of identically 0. The accepted deduction follows a straight line. Because we observe zero tidal deformability, the object must be a standard black hole containing a central singularity. Kgr's paper argues this deduction is a non sequitur. It conflates the geometry of the exterior with the physical reality of the interior. The vanishing of the tidal love number relies strictly on the regularity and vacuum nature of the space outside the horizon. The math guarantees a K2 of 0, regardless of what structural physics exists deep inside the core. Concluding that a null tidal measurement proves the existence of a singularity is a logical trap. It leaves the door open for alternative interior models that share that exact same vacuum exterior, but replace the singularity with a highly structured core. This chart displays mass radius curves for quark matter equations of state, like the MIT bag model. Notice the orange band representing the mass gap region. Realistic quark matter equations fail to support compact structures above 3 solar masses, falling entirely short of observed black hole masses. To reach these higher masses without forming a singularity, the local gravity of quantum vacuum framework proposes a different mechanism. It suggests that gravitational collapse halts dynamically when the material reaches a specific threshold, known as the chiral restoration density. At this exact density, the interior transitions into a frozen star, a Lorentz scalar vacuum state, operating under an equation of state where the pressure parameter W equals -1. This extreme negative vacuum pressure provides the exact outward stress tensor required to halt gravitational collapse entirely. Instead of crushing inward to an infinitely dense point, the object settles into a uniform regular de Sitter core. Since quark pressure alone cannot hold up stellar mass black holes, this vacuum halt mechanism provides the necessary physical support. The challenge then becomes connecting this highly pressurized core to the empty space of the outside universe. The Kgr radius defines where the uniform interior de Sitter core meets the exterior space. According to Proposition 1, these metrics match algebraically, making the transition perfectly continuous. This occurs automatically. No gradient layer exists. Immediately outside the Kgr boundary is a perfect vacuum.
The direct consequence of this pure vacuum exterior is simple. Because there is absolutely no matter outside the Kgr radius, there is no physical material to be tidally deformed by a companion object. This brings us right back to the Binnington-Poisson theorem. Because the exterior is completely empty, the K-limit model guarantees a tidal love number of exactly 0, identical to the standard Kerr prediction. Standard general relativity and the K-limit model are observationally completely degenerate at the tidal level. Measuring the deformability of a black hole will consistently return 0, making it impossible to break the tie using this specific test. This realization represents a crucial formal self-correction. In an earlier iteration, Kgr hypothesized that supermassive black holes would retain a deformable transition layer, suggesting that future missions like LISA might actually measure a tidal love number greater than 0. That initial assumption was completely physically flawed. The controlled derivation we just walked through proves that maintaining a uniform density out to the Kgr radius leaves zero deformable material outside the core. This rigorous recalculation was directly motivated by critique from physicist Daniel Brown at the University of Utah, who pointed out that the earlier empirical claims relied on scaling arguments rather than controlled mathematical derivations. As a direct result of this check, Kgr explicitly withdraws the prediction that the LISA observatory will detect tidal deformability in supermassive black holes. The paper also acknowledges a broader network of physicists whose correspondence helped shape this rigid framework, including Stanley Brodsky, Craig Roberts, Alexandra Dewar, George F.R. Ellis, Thomas D. Cohen, Joan Sona Parakawa, and Franz Klinkhammer. Publicly withdrawing a flawed discriminator is a vital step in the scientific method. By removing a prediction that would have been identical across both theories, the framework sharpens its actual empirical exposure, leaving only the tests that matter. If tidal deformability cannot differentiate between a singular black hole and a regular frozen star, what physical mechanism actually can? The framework leaves one distinct binary discriminator, a predicted continuous gravitational wave signal known as Kgr-Radiation. The Kgr radius isn't static. The chiral surface sits at a flat critical point, meaning the outer shell executes a rapid, rhythmic limit cycle. At the microscopic level, the extreme outer boundary layers of the star continuously cycle back and forth between states of confinement and deconfinement. This continuous bulk oscillation physically modulates the object's quadrupole moment. That oscillation pumps a steady, classical, narrow-band gravitational wave out into the surrounding space. This active, oscillating surface stands in stark contrast to the absolute dead quiescence of a standard Kerr interior. It establishes a clear, testable physical difference in how these two objects behave when isolated in space. The math scales mass against observed frequency to the -2/3. Stellar mass objects emit Kgr-Radiation into the 20 Hz LIGO band. Sagittarius A star emits at 7 mHz for LISA. Ultramassive black holes reach the pulsar timing array range. General relativity predicts zero continuous signal. Upcoming observational campaigns must pivot. Instead of searching for an absence of tidal stretching, the true discriminator is a binary search for these precise narrow-band signals. If next-generation detectors find Kgr-Radiation, the singular black hole model is refuted. If the cosmos remains completely quiet, the K-limit picture is falsified. The trap of zero tidal deformability is bypassed, and the true test begins.